Okay. Welcome, everyone. Tonight, I am going to talk about black holes. And more specifically, I'm going to talk about Planet 7 star. That is not a star, but it's a superstar. I would say nowadays it is definitely one of the biggest black hole superstars, and I will talk about why in the astrophysical community it's considered so. So let's dive right in. Here is the picture. This is the first ever black hole image. And this came out in 2019, April 10, 2019. So I was in my last year of high school, and I remember very vividly thinking, wow, this is insane. It would actually be amazing to work studying these objects. But what do we actually see here? That's a good question. Because we know that black holes don't really emit any light. So what do we see? And how can we take such a picture? How could you take a picture of such a tiny object far away in the sky? Tiny, we'll see what I mean by that. And yeah, what properties can we infer from such an image? So this is go back a few sentences. I'll give you a brief history of black holes. MX7 specifically is now studied today. That was brought forward independently by two astrophysicists, well, two astronomers, Mitchell and Laplace, in England and in France. And they just thought about the idea that you could have an object so massive and so compact that even that its escape velocity would be larger than the speed of light, so that you wouldn't be able to observe anything from this object. And this was dubbed dark stars at the time. But the idea didn't really catch on, and it was just a funny thought process, let's say. But things changed in the 1900s. So Einstein published at the beginning of the century his famous theory of general relativity, and very little time after, Kurzweil actually provided solutions to the field's equations that are equations which link the mass and energy of an object to the geometry of the spacetime around it. And he solved these equations for a specific case of a spherically symmetric and non-rotating object. And when doing so, he actually came across certain singularities, and in particular, a singularity at a radius that we now call the Schwarzschild radius, given by this formula here, twice the gravitational constant times the mass divided by the speed of light squared. And at the time, people didn't really understand this. They kind of didn't want to take it seriously. Einstein himself said at the end of a paper, oh, the singularities are not physical. So they were mostly disregarded. People looked at what happened further away than this radius from this object, mostly. But now we know that this is actually a very important quantity that defines a surface that we call the event horizon, which is the surface of black holes beyond which we cannot get information. But at the time, this was just theory, and this wasn't necessarily taken seriously. Things started changing in the early to mid-1900s through progress in other areas of physics, including, for example, quantum physics. And at the time, people had puzzles related to white dwarfs, so massive stars that had come to the end of their lives, and also neutron stars. And people started understanding that these could compensate the force of gravity at the end of a star's life when the radiation cannot compensate it from collapsing completely onto themselves, thanks to certain types of pressures that we call degeneracy pressures. For example, neutron degeneracy pressures. But people were also aware that above a certain mass, 3 solar masses, actually nothing will prevent a star from simply collapsing onto itself at the end of its life. So you have a diagram that's pretty nice because it was somewhat handmade at the 1995, and you can see how the black holes already appeared in these diagrams. And at the end of the 60s, things really started to change. People understood that black holes were not just a funny thought experiment, or that, for example, the Schwarzschild radius might not just be a singularity that cannot physically make sense. Because people started finding, for instance, solutions to rotating black holes. This was Kerr in the 1960s, and we expect everything in the universe to rotate, right, including black holes. And also, a lot of theorems were proposed and that were proven at the time by, for instance, Israel and Carter. And this is the no-hair theorems. The no-hair theorem sounds funny, but the idea is just to say black holes don't have hair. Black holes are very simple objects. They're the simplest possible objects maybe in the universe that can be entirely described once they're formed by 3 parameters: their mass, their spin, how they rotate, basically, and their electric charge. So they were starting these objects to become not just theoretical objects, but to make sense potentially also physically. And you can see here the first simulated image of a black hole by Thevenet in 1979. And you can see that this already starts to resemble very closely to what the EHT in the Event Horizon Telescope, the image I first showed, found. The observational era of black holes really kind of started in the 70s. So it started with what we call stellar mass black holes, which are black holes of a few times the mass of the sun, in this case, about 20 solar masses. And this came with the discovery, thanks to the advances of X-ray technology, of an X-ray source called Cygnus X1. And Cygnus X1 shows very fast flashes of X-ray light, so in the X-rays. And people were also able to observe a companion star, so a star that appeared to be in the same location as the flashes, and they realized that there was this very massive star that was rotating, that was in orbital motion that you can see with this plot with the radial velocity over the orbital phase. And this orbital motion can tell you a lot of things about what the star is orbiting, and in particular that it's orbiting something that is very massive, but it's orbiting in a small region. So at the time already, people were pretty certain that this could be nothing else but a stellar mass black hole. So this was the first generally accepted indirectly observed black hole. And NASA has a series of galaxy of porous posters, for which it has one for Cygnus X1, this black hole that was the first one to be considered. If you like posters, I recommend you go and check it. But this was for stellar mass black holes, and things become interesting when we look at other types of possible black holes. And this started in the 50s, 60s, so if we go back then, radio astronomy became big. So instead of X-rays, now if you look at the radio, so low frequencies, objects that were called quasi-stellar radio sources, they were named this because they looked like stars, but they were really not. So quasars, in short, were discovered. So these were point-like sources, but people realized that they were extremely, extremely far away, so they had to be very bright. And you can see, for example, here, the image by the ESA and Hubble of something that really looks point-like. You can see it with the diffraction pattern. But if you use a coronagraph and you hide the central part, you see a galaxy halo surrounding it. So people understood that these quasars and other objects that were starting to be observed at the time were actually extremely bright and distant nuclei of galaxies. And we call these active galactic nuclei because they're active, and I will explain more also why we call them active. And this is most likely powered by matter that is infalling onto a supermassive black hole that would be at the center of such galaxies. I will stop here with the history and skip to M87. So why M87? First of all, who is M87? So M87 is short for Messier 87, and Messier was an astronomer who did a list of sources in 1781 in order not to confuse certain fuzzy objects or nebulous objects with comets. And MX7 was the 87th such object in the catalog, so this is where the name comes from. And interestingly, in 1918, Curtis wrote a paper in which it described the appearance of a lot of objects, and MX7 is one of them, and it said that he saw a curious straight ray. So he saw something similar to what you see in this image, except this is a much more recent image by the HSC. He saw this sort of line that connected all the way into the galaxy. And this line, we know now, responds to a jet. This is a powerful relativistic jet. It contains plasma matter that goes at speeds close to the speed of light that is being ejected outside of the galaxy. And in the 1940s to 60s, people also started observing the radio and the X-rays, and they saw that sources in the radio called Virgo A and in the X-ray that they called Virgo X1 matched the same position and corresponded to M87. So it became clear that M87 corresponds to this supergiant elliptical galaxy that is pretty close to us. It's 16.4 megaparsec away. I mean, close. It's far away, but it's the local universe. So compared to a lot of such objects, such active galactic nuclei that we see are much further. And it's one of the largest and most massive in the local universe. So for a long time, it was expected to host an active galactic nucleus that you can see here represented. So the idea is that at the center of these galaxies, you have these supermassive black holes that can be millions, billions of times the mass of the sun, surrounded by what we call an accretion disk. So matter being accreted, falling onto the black hole and feeding the black hole. There can be a lot of other processes around, but what we're interested in is mostly this and these relativistic jets that are being launched from it, and that we see very well and very beautifully in AMX7. So, okay, great. We expect to find a very massive black hole pretty close to us. But how can you observe it? Because this still corresponds to trying to, if you want to really resolve the central region where you find a black hole, and you can estimate the mass, you can estimate the Schwarzschild radius, so the size approximately of the event horizon. If you want to see this, you still need to get to very, very high resolution. So you need to be able to see something extremely small in the sky, about a golf ball on the moon. Okay. So how do we do this? We construct a telescope the size of the Earth. We can't really do that, can we? But we can be more clever and use what we call very long baseline interferometry, or VLBI. And this is a technique that basically allows you to observe features with very high angular resolution by using not just one telescope, not just one dish, but a lot of telescopes, a lot of dishes that are separated by long baselines. The baseline is the distance between the telescopes. And what basics of interferometry tell you is that you will achieve higher angular resolution, so this theta will become smaller if you increase either the diameter of one telescope, or in this case, the baseline between telescopes. So if we want to put telescopes, well, we put them on Earth, and we put them as far away as we can. And that's the EHT, the Event Horizon Telescope. This is a collaboration that includes a lot of telescopes that you can see in the map on the left, all over the world. And this array has an effective aperture, the diameter of the Earth. Of course, you don't have a dish the size of the Earth, so you don't get all the light, and you need a lot of data analysis and techniques in order to be able to reproduce the images, to obtain the images in the end. But this allows you to observe very fine details in the sky. And so in 2017, during quite a few days, the EHT finally turned to look at MX7, this massive galaxy that should host a supermassive black hole. And this is what they obtained. So this is the image they published 2 years later, because as I said, the data treatment, the data analysis is very complex, and they wanted to make sure that this was actually what we observed. But this is indeed the shadow of this supermassive black hole MX7 star. If you're curious as to why we put a star, we usually put a star. We can talk about this after, during the camp. And the estimated mass of this object is 6.5 billion solar masses. So this is also one of the most massive known black holes overall. And this is, again, the first direct visual evidence of a supermassive black hole. So we've made it, and if you want to have a reference in size, here is a small sketch of the solar system. So you see the sun in the center, where you have the depression, the shadow, and you see Pluto's orbit and Voyager 1, which is like the furthest we've ever launched anything. And this barely reaches the end of the shadow. So this is really a supermassive black hole. But again, what do we actually see in this image? We said black holes don't emit light. And in fact, what you see is not light coming from inside the black hole at all. You see the shadow. So the shadow is the depression that you see, the reduced intensity in the center. This is where no information reaches. And all the red ring that you see around is the plasma. There's, we said, matter that infalls around the black hole. And this hot plasma will emit radiation, and you can observe this radiation. Actually, we're not entirely sure what this radiation comes from. Is it mostly the accretion disk? Is it dominated by the base of the jet? It's still a matter of debate, but it is plasma that is around the black hole. And an interesting question also might be, why do we see this ring, this exact ring that we also saw in the Luminet Luminet picture that I showed earlier? Why do we expect this? This is caused by gravitational lensing. So the idea is that around such a massive object, gravitation is extremely strong, the gravitational forces. So you will bend light, the photons will be bent. And for instance, something that is beyond the black hole that you wouldn't be able to see, let's say if it's something behind my hand here, in this case, the photons can be bent and can actually reach us. So you can see some of that light. So you will see a ring around the black hole and not just, for example, one side of the torus, if this was coming from a torus. And you can also see effects that might be caused by relativistic beaming. And the idea here is that the matter that is orbiting around the black hole is moving at very high speeds, very fast. So you have a Doppler boosting. So when the light is coming towards us, for example, on one of the sides, it's being boosted. It appears brighter, while on the other side, it appears less bright because it's moving very fast away from us. So these are all effects that were predicted by theory and that we actually can observe. Actually, the EHT didn't stop observing things in 2017. It's done other campaigns. And this is an image from 2021. So this is from the 2018 campaign, Paloma. And in this case, they also measured polarization. So this tells you how the electric field is oriented. And this tells you something about the magnetic field around the black hole. And in this case, what they found is that you have very strong magnetic fields around close to the horizon that are organized. And this is interesting because it can help us understand better how, for example, the jets are launched, because there are a lot of effects from magnetic fields to be taken into account. So we're focusing on the radio picture because it's an amazing result. It's a pretty picture, but actually we see MX7 at all wavelengths. So we call this multi-wavelength astronomy when you use different types of different wavelengths to be able to tell something about the object. So you can see here a composite image where you have the radio on the side, so the EHT image of the shadow, and at different resolutions you can see larger parts of the jet all the way there. Then you have the opticals. So for instance, this is the HST image. You can see again the core and the jet, and then you have the X-rays up there with Chandra. And this is the Fermi telescope. So this is the telescope on orbit that detects gamma rays. And these are Cherenkov telescopes. These are telescopes on the ground that can detect gamma rays. Actually, gamma rays don't cross the atmosphere, luckily for us, but we can detect them in other ways, and we can talk about this as well during the time if you're curious. But the idea is that you can really see MX7 at all wavelengths, and each wavelength tells you something different. But what this tells you, first of all, is that you have non-thermal processes, so you have accelerations of particles that leads, for example, to the observation at the highest energies. And this is one of the open questions that we have today, and that I'll come back on. But because MX7 is so close and we can resolve the jet so well, for example, you can see that we see a lot of structure in the jet. We see knots, and not only the core, but also the knots along the jet that may change or return or not. This helps us probe a lot of different phenomena and physics that are involved, which can be linked to theories of gravity. So, for instance, using images like the shadow, plasma physics. So, for instance, how the jet is launched and what it contains, etc. Processes of particle acceleration. MX7, I said, is a superstar of black holes, and not just because it was the first one that we were able to image, but also it was the first radio galaxy that was observed in gamma rays. So this was in the 2000s, it's relatively early. Gamma rays are at the very energetic end of the spectrum, and at the very high energies that were defined as larger than 100 gigaelectronvolts, so this is very energetic, you sometimes observe flares from this object, which is an increase in flux by, let's say, an order of 5 or 10, but on very short timescales, like a few days. And so this was also for the first radio galaxy for which we saw this, and this implies that the radiation is very high energy. Radiation is coming from very compact zones, but we don't really know where it's coming from. Where does this high energy emission come from? And also, what are the mechanisms that can accelerate the particles and power these fast flares on these short timescales? You can see on this light curve, so you see over time how the flux changes at different wavelengths. And the top curve shows you the highest energies, so these very high energies. And you see, for example, these very rapid flares that happened in 2005, 2008, 2010. So we regularly see this, and we still don't really know where it's coming from. We have some clues. We wonder that maybe they might be coming from close to the core, in a region where the jet is being launched, or further downstream, further down along the jet. And This might come from processes like shocks, in which particles can accelerate, or events that we call magnetic reconnection, that I'm not going to go into the detail here, but it's linked to magnetic fields rearranging themselves and releasing magnetic energy into the form of acceleration of particles. So these are candidates for explaining these flares, and it's one of the questions that is still open today. So I went through a lot of different topics, but the idea is to give you an overview of why MH7 is so famous and why do we still don't know so many things and what are these things. So where do we stand now? We went from black holes that were purely theoretical objects to actually observable realities. We now have quite a lot of indirect evidence and some direct evidence for the existence both of stellar mass and supermassive black holes. And I didn't talk about gravitational waves at all today, but those are also extremely important. And we enter the realm of multi-messenger astrophysics, where we use different messengers, so not just light, not just the spectrum that I showed, but gravitational waves or particles. And gravitational waves have actually allowed us to see mergers of black holes. So this is something that you could definitely look into. We've also observed the shadow of two black holes. So I've been a bit selfish here, and I've only talked about MH7, but actually we have observed also, EHT has observed also Sagittarius A star. So we see in short Sagittarius star, which is the supermassive black hole at the center of our galaxy. It's way less massive than MH7, but it's much closer to us, of course. It's in our own galaxy. So it was observed, and it actually shows quite a lot of different interesting properties. We know their masses. We don't know their spins. We don't know how much they rotate. This is a very big question that we all have, and the community, I can tell you, really wants to know. So there's a lot of projects ongoing to be able to find answers to these questions. We also don't really know how jets are launched. There is a lot of active galactic nuclei that have these jets. MH7 is one of the most famous ones, and it's a great probe for understanding how, because we can see it so well, because it's close by. And where does this very high energy come from? How are the fast flares produced? These are some of the questions that we still have, despite all the progress that's been made. And there are even more exciting questions that await a lot of exciting answers. So I hope some of you will join in this trip to answer all the questions around black holes. Thank you.